welcome to Module 26, or Perception Pitfalls. We're going to extend some of the topics that were introduced in the previous module on visualization grammars and continue mostly to talk about how to convey data science information, data-driven information graphically through visualizations. But from a certain perspective, this is going to be potentially one of the most important modules that we've seen so far in this course. Because to such an extent it transcends sort of low-level details by themselves, which is still important, but it also speaks to a wider societal issue of how data science can be used to misinform the public. And obviously we're living in a time when misinformation and perhaps lack of critical thinking abilities is causing extreme challenges around the world. So we're not going to address all of those obviously in this one course. It's going to be really focused on issues related to improper data visualization. But along the way, dealing with those kinds of problems will mean confronting challenges of human cognition and human biases. By the end of this module, you should be able to explain how human perception can be exploited or confused by certain visual encodings. You'll be able to diagnose common deception patterns in charts. You'll be able to compare alternative visualizations on the same data and then to justify which one is more honest or which one's more interpretable. You'll be able to implement small Python examples that illustrate misleading or truthful design choices. And you'll be able to apply an ethics-oriented checklist when creating your own plots. So in Module 25, we actually saw Bertin's variables. I mentioned them briefly, but here they are just visually. We talked about position of marks, the size of marks, shape, value, hue, orientations, and textures, for example. Now, we kind of use them, but each of these variables can interact with each other in ways that might complicate perception, and I want to give an example of what I mean by that now. So I'm going to show a series of 3 images, and there's going to be a description at the top for you to find a particular object, and I want you to try to find it as quickly as possible. Okay, so you can play along at home or wherever you're watching this. Find the red one. You've probably already found it. It's right there. Next graph. Find the circle. I'll let you think about this for a little bit, but probably by now you've already found it. It's up here in the upper left. Now finally, I'm going to change 2 variables at once. I'm going to change the color, and I'm going to change the shape. And I'm going to try to find the conjunction of both of these things. Find the red circle. You might have found it by now. I think by now you've probably found it, but you can see that even in this simple task, these 2 variables intersect in a way that for most of you probably have made this last task a little bit more challenging than the first 2. Right? It's harder to find both something red and something circular when we have this kind of messy distribution like we have here. So this is based on classic work of feature integration and pre-attentive processing and visual perception guidelines, which you can read about here and here. So there's a bunch of key concepts here. The first one is perceptual channel, a visual property that our brain picks up quickly. This is like the position of something, the length of something. Human brains are biased to pick up on these channels relatively quickly. We can see big differences in color, for example, very quickly. A pre-attentive feature is something that our visual system notices almost instantly without any conscious effort. So like the one red dot, the back part of your brain, the occipital lobe of your brain, which does a lot of the visual processing, automatically does some categorization and some pre-processing for us before our cognitive conscious minds take over. So the pre-attentive feature means something we attend to before we consciously attend to it. A perception pitfall is a systematic way that a chart can lead the viewer's eyes and brains to the wrong impressions. So if you know like the biases that humans have in terms of our pre-attentive features, a mischievous person or a group might try to take advantage of that to lead us astray. A misleading visualization is a plot that uses real data. So obviously using incorrect data or made up data is outright fraud. But you can still make graphs that use real data, so you wouldn't get necessarily in trouble for it or legally, but it would still misinform, right? This is the kind of the gray area that it's not so gray in my opinion. Like it's still misinformation, it's still lying with visualization, so it's still ethically very negative, but it's a different order than outright fraud. And then finally, ethical visualization. Ethical visualizations are plots where design helps the viewer see the true message of the data I say true, I should put it in quotes. Like I'm going to emphasize a few times, we should never think we absolutely have the truth in hand. We should always try to be seeking the truth. But generally, there's going to be some trends which are less ambiguously true. So we're, as much as possible, can we visualize these less ambiguously true visualizations without having to hide uncertainty or exaggerating effects. Like if we're uncertain about something, we should make that clear as well. So our visual system and our cognitive system are basically pattern machines. Our brains are computers too, just computers of a different type than we're used to in front of us. So they're very good at seeing trends and clusters and outliers and groups. But because of the way our brains work, there are some predictable bugs. We overreact to color and contrast. I'm talking visually here. We can easily misjudge areas, misjudge angles, and we can easily be tricked by context and optical illusions. So a good visualization knows these biases of the human brain and might use them on purpose to help guide viewers to the right solution. But also we want to avoid or at least clearly flag where there's weaknesses. So if it's a visualization that possibly ignores these bugs, then that might lead to improper visualizations. So I mean, we already know a lot of optical illusions, so I don't need to spend too much time on this. A color illusion is one in which we have like two squares. Which of these two middle squares is the darker one, which is the lighter one? It's kind of easier to tell what's going on here than in some other visualizations. This is just something I put together in Python. The inner square on the left might look light, the inner square on the right might look dark, but the RGB values of these inner squares are exactly the same. It's just because they're contextualized by these outer squares, which are darker or lighter respectively, that our perception of the inner square changes to some extent. You've probably seen lots of examples of this. And then the famous Muller-Lyer illusion, where which object is longer, the top one or the bottom one, in terms of just the horizontal component. Well, the top one might look longer because it has these kind of accoutrements that seems to stretch it a little bit, and these arrow-looking things seem to bend it towards the inside. Even looking at this right now, like I can kind of very see there's a slight difference. The ones at the bottom seem a little bit shorter than the one on the top. Even knowing that this is an optical illusion, your brain can still be fooled. So we know this illusion already. This is just to emphasize our human brains are not gold standard oracles. We can easily be led astray. And we can be led astray normally by, in this case, context. So in one side, the context is the hue that leads our processing astray in terms of the hue of the inner square, and then we also have this illusion of context, which helps lead us astray to decide which of these lines is longer or not. So in both of these cases, like the physical measurement might be exactly the same, but our perception is not. Like what we see. There's a saying that we see things not the way they are, but the way that we are. So we see things based on our own mental filters, and that can lead to all kinds of problems. Sometimes they're cute, little fun, childish games like this, but as we'll see, sometimes it has much more serious consequences. So one of many warnings, if your chart relies on people being perfect judges of things like angles, areas, colors, especially if you have context, then you're going to have a bad time. So, what are humans good at? What are they less good at? Well, we're pretty good at position as long as the scales are common and are appropriate. Even position on somewhat non-aligned scales we can be good at. So if you have like a linear scale versus a logarithmic scale, we can still sometimes come to the right conclusion fairly easily. Length we're normally good at, the previous example notwithstanding, but we're pretty good at judging lengths and distances. Again, we're going to see examples of how to break this. We're okay with regards to angle and slope, but in simple orientations. But the difference of like 45 degrees we might be decent at, but anything beyond that maybe less so. Again, getting pretty bad now. The areas of things, judging the exact area of a circle or a filled region or a volume, or even the lightness or darkness of something, we're pretty bad at. Sometimes this can be because of like environmental things. If we're reading something in a dark room versus a light room, this can change our perception. But just generally, humans aren't very good at judging area or volume. And we're very bad at color, hue, saturation. Slight differences in texture or patterns we can also have a lot of trouble with. I'm just noting that there's a lot of classic work on perception experiments and the effectiveness of the different channels we talked about in Module 25. So you can grab these and read about them. And there's a lot of new work that also shows that how good these channels are in terms of our dealing with our perceptual strengths and weaknesses. This can actually vary across the different tasks we're trying to perform. Again, in Module 25, we talked about tasks like finding the minimum, finding overall trends, and there's subtle ways that we can manipulate people that way or be manipulated that way. These are all guidelines, they're not laws. This is all science, so everything is couched in caveats and statistics, but generally the relationship between tasks, contexts, and design matters greatly. This is kind of this is why I mentioned this. This presentation is going to be important. We're going to talk about ethics and ways in which visualizations can lead us astray, like this duplicitous gentleman over here. So, is a saying. I think it's André Gide who said this. Like trust those who seek the truth, but doubt those who find it. That's what we're trying to do. That's what we're doing as good scientists. Like we're always trying to find the truth. But whatever we come up with, we can never be sure that this is the absolute truth. There's always a possible thing we missed or something we're misinterpreting. It's important to be curious or skeptical, depending on how you want to phrase that, and never assume that we've finalized our interpretation. We finally obtained the one truth that we now need to spread amongst all others. Our world is full of these arguments and interpretations, and a lot of them these days are pushing some agenda. Sometimes they're purposely pushed through, like state-based misinformation is purposely trying to mislead us. And then there's sometimes people who are themselves just misled and they're trying to convey something that they truly believe in, but they do so in ways that are not entirely honest. And sometimes people use statistics in this way. You might have seen these things on YouTube where you have a group of people sitting around one person and they have these kind of pseudo debates, which are some of the worst debates I've ever seen. But a lot of them involve people who seem to think that they're pretty smart, and they use statistics and they pull numbers out of hats and so on. So those kinds of pseudo debates are ways in which statistics are misused to push an agenda, to push a particular point of view and ignore other points of view. So not all of the examples I'm going to show you are necessarily outright lies. I'm going to frame them as lies because they act as if they're lies, and they might as well be. But basically, they're going to push conclusions that the data are probably not going to support in most cases. I want to emphasize this again. Data visualization can still be deceptive, even if you're using the same data, the real data, right? So sometimes people are caught faking data, like they produce data out of thin air, and then they put that into a report. That is outright fraud, and that carries all kinds of serious sentences along with it, or any kinds of punishments along with it. That's clearly deceptive if you just invent data, and pretend it's not made up. All of the examples that I made for the visualizations in this class is perfectly reasonable because it's obviously make-believe, just to make that absolutely clear. But sometimes you can have a real set of data. Nothing, even the pre-processing is done correctly, outliers are removed, all those steps are done correctly, but just the visualization step pushes an agenda and pushes a particular interpretation on the viewer in a way that itself is still deceptive. So this is all about protecting yourself and then also helping others protect themselves as well. Okay, this is, I view as not just a little cute area of data science or human-computer interaction. This is like a fundamental aspect of what it means to be a human in the 21st century. So here's lie 1A. So we're going to look at axes of graphs, like these mostly, in this case, a bar graph. These axes, in this case, is too narrow. So here we have this graph pushed by a particular source of, a particular channel. I was going to say source of news. So you have people on welfare, and you have people with a full-time job, and then you have measurements that kind of compare these individuals. So looking at this graph, again, if you're barely awake, you might look at the graph on the left, ignore the numbers because numbers are complicated. Not really, but you know what I'm saying. And see people on welfare drastically overwhelms people with a full-time job. And if you're one of these people who's like grumpy about people getting handouts from the government or something like that, then you might look at this and see like, wow, the world is crazy. There's only a small number of hardworking people and everyone else is just ripping everyone off. That's the main message you'd get from this graph. That's the agenda being pushed on you. And what's going on here is there's no y-axis. So first of all, it's not exactly clear what's going on here. But obviously things are being truncated. So the difference between 108.6 and 101.7 is still pretty significant. I'm not going to lie about that either, but like it's not orders of magnitude different like this graph might seem to indicate. Okay, and I'm not even sure what other kind of manipulations of the data had to go into this graph beforehand, but clearly there's this graph and it was cut off, so only the tops were shown, and then the differences between these graphs were emphasized to a point that pushes an agenda. That's when things are too narrow. You've zoomed in too much and you've removed useful information. You can also zoom out. So this individual posted some social media nonsense talking about rises in CO2 and so on. So here's like global temperatures over time going back to the late 19th century. And looking at this perspective, you can see that, well, there doesn't seem to be much of a change at all in terms of global temperatures. So like, why is everyone complaining? There doesn't seem to be a problem. Things aren't changing that much. But what's going on here is this might be real data, but the person now zoomed out too far to a point where like the scales are meaningless. Okay, so we're not zooming in to make the differences massive, like in the previous example. Now we're zooming out to hide differences within the small number of pixels that are now going to differentiate these two numbers. The y-axis goes from 0 degrees Fahrenheit, which is like an incorrect measure of temperature, but whatever, from 0 degrees Fahrenheit to 120 degrees Fahrenheit, right? If this is a global temperature and the average is 120 degrees Fahrenheit, like this is a much bigger problem than anyone we're currently facing currently. This is an unrealistic view of the data in terms of what constitutes regular climate on our planet. So this person wanted to hide differences. They zoomed out so differences were now more or less invisible, but they did so in a way that technically might not have faked any data, but is still being deceptive. So here's this overall example. We have interest rates. Interest rates keep on coming up in the news about as a way to represent the health of an economy. And depending on what your point of view is, you might want to look at the graph on the left or the one on the right in order to push some particular agenda. This is the exact same data. On the left, I've zoomed in to make the differences seem big, and on the right, I've zoomed out to make the difference seem small. Like an interest rate of 0% is basically impossible. So like zooming out to this extent is ridiculous. Yeah, like if I want to say that interest rates are getting out of hand, I might look at the one on the left. I should have changed these numbers here. This is from a previous class I taught. Yeah, like I can see, wow, it's going up and up and up, these interest rates, like will it never end? And it kind of conveys the message that interest rates are rising uncontrollably. If I want to say, no, everything's fine, there's no difference, everything is stable, then I'd look at the graph on the right, and that would be my message. So again, depending on your point of view, you can take the same data and tell two drastically different stories that would lead to drastically different conclusions or steps you might take if you're the Bank of Canada or whatever. So the first collection of lies involved taking the axes, the y-axis in particular, and zooming in or zooming out to an unacceptable extent. The second lie is still going to involve axes, but it involves kind of changing them. So going from linear and log and back and forth. Okay, so you might have heard of Purdue Pharma. They launched OxyContin, I think way back in the 1990s. And they aggressively, like they had different versions of it, and they aggressively marketed it as safe. It's perfectly safe. And a lot of the basis for saying it's safe was based on this short New England Journal of Medicine letter that downplayed the risk of addiction. So here's a lot of references that you could look into to read about it. So this last paper here by Porter et al., like 1980, is not about OxyContin specifically, but it covers the same kind of topics. So, I mean, obviously, like these kinds of opioids is a major problem across many countries in the world. I'm not going to get into it too much, but try to stay out of the political thing. But sometimes, a decision maker might point to certain regions or nations or individuals even as sources of this scourge, and they might ignore, in this case, corporate interests that pushed opioids in the first case. But that's another story altogether. The reason I'm mentioning this now in particular is these two graphs. If we were to look at these two graphs and look at kind of the dosing as these nominal categories, so each of these line graphs represent a different amount of dosing. You have hours proceeding linearly on the x-axis, but the y-axis is different. So the y-axis on the graph on the left is, both of them are in terms of oxycodone concentration, how concentrated something is, and then how it deteriorates over time. On the left, the graph is logarithmic, so it goes from 1 to 10 to 100. So like visually, the difference between 1 and 10 is the same as between 10 and 100. And on the right, it's linear. So 0 to 20 to 40 to 60 to 80, these differences visually are equivalent. And you can see on the right, there seems to be a very massive difference in terms of the concentration for this 160 milligram version. It's far different than these others at the bottom. So 10 milligram, 20 milligram, 40 milligram might have been approved for use, and they have small amounts of concentration, 3 times less at its peak than this 160 milligram version, okay? But the difference between the 160 milligram version and the 40 milligram version is almost completely squashed out when we kind of stretch nonlinearly the y-axis to go from linear to log. Right now, 160 milligrams looks more or less equivalent to 80 milligrams, not that much more than 40 milligrams, not that much more dangerous. So it might be easier to get the drug approved because it seems to be not that much different than previously approved drugs. Okay, this is simplifying things to a large extent, obviously, but you can see what's going on here. And this was found to be like the executives at Purdue were found to be culpable for all kinds of misleading activities related to OxyContin. And part of the story was that how they tried to sell the story that this is safe was based on this graph, which I believe this particular graph appeared in this New England Journal of Medicine letter. This tells a couple of stories. So first of all, something as simple as changing the scale can convey very different outcomes. It's dangerous on the right, it's not dangerous on the left, same exact data. It also highlights something that I occasionally come back to, which is that even if something comes from a very reputable source, the New England Journal of Medicine is one of the most highly cited, most impactful journals in the world. But regardless, that doesn't mean that everything it publishes is necessarily correct or can be interpreted as being correct. So again, if someone chooses a scale of evidence, like the wrong population, a too short term a study, a cherry-picked statistic, some nonlinear transformation of the data like this can make a dangerous product look safe. This is essentially lying with numbers. Again, people were found to be liable for these lies, and but the result this is part of the reason why we have the opioid epidemic we have now is because of lying with statistics. Again, so I can't emphasize this enough. This class is not merely about, how to perform certain tasks in Pandas and Python. It's about understanding that doing that has real world consequences that can be massive. And I really hope that's getting across. Along the same lines, kind of modifying the axes. This is lie 2b. Now we're going to go from absolute to relative differences. There's this link over here from Oxfam. This complains about the so-called elephant graph. So originally there's another citation which was trying to push the agenda that the lower economic status individuals were suddenly doing very well in the economy. Okay, so they did so by looking at this blue curve. This is called the elephant graph because it looks like an elephant with his trunk sticking up here on the right. And it shows different percentiles of groups of people. So people in the lower 10% in terms of income. Those kind of buckets through binning. And then you have the percentile income growth. So in the lower 10%, how much did their income grow between 1988 and 2008? And they did this for each of the different buckets over here. Okay, so looking only at this blue graph over here, you would interpret the following. You'd look at, well, from the decades between 1988 and 2008, certainly the top 1% saw their income grow by over 60%, which maybe is unfortunate, when you compare them against the people in the 80th to 90th percentile range. But look, like everyone below the 80th percentile had these massive gains in their growth. So things were actually very good over this time. It was a time of growth for the relatively disadvantaged. And we should be happy with ourselves. Our economic policies are working for everybody, and we should be pleased. Okay, so that's what we get from the blue curve. But if this is all in terms of percentages, so the lower 10% had a 25% increase in their income over these 2 decades. And the top 1% had a 65% increase in their income. But 65% of, you know, I don't know, millions of dollars is obviously much greater than even 65% of tens of thousands of dollars, right? So if you look at absolute terms, which is this green curve, which is the topic of this cited source down here, you can see that the story might be somewhat very different, right? The rich got a lot richer, and everyone else, more or less, you know, in absolute terms, stayed the same. There's a little bit of a jump here, but yeah, there's a very different story here. There isn't this huge, people climbing the social ladder that the blue graph seems to indicate. Again, changing the scales in terms of absolute versus relative. This is a country near Canada that you can see maybe during an outbreak, confirmed cases by region, and the darkness here indicates the number of confirmed cases, from 1 to 10 cases in yellow to more than 100 cases, more than 101 cases in dark brown. Looking at this graph, the first interpretation is, oh, well, like there seems to be a lot of cases around New York and Boston, the Floridian cities, San Francisco, Los Angeles, Seattle. And then a certain interpretation might be, wow, these major cities certainly are problematic, and isn't life better in these rural areas, where cases aren't as highly confirmed. But these are absolute numbers, right? So the number of people who live in New York City is, I believe, on the order of 15 million people. So of course they're going to have more than 101 cases, and compared to a town with only 500 people in it, right? So absolute numbers don't tell the whole story. We're going to see a real example of absolute and relative being transformed between one another shortly. But yeah, like the story that big cities are huge problems in terms of confirmed outbreaks. Obviously, if people are densely packed together, then it makes infection harder. So I'm not trying to say things are totally black and white or one way or the other. Obviously, big cities have certain challenges that rural communities might not, but this story that just big cities are inherently bad in terms of confirmed cases doesn't tell the complete picture. Whoever drew this graph should have used per capita or relative scores. Lie 2C, again, it changes scales in some way. Here, this graph talks about oil in the water, like oil being seeped from various sources. So 63% of oil in the water comes from natural sources, 4% from transportation, 1% from offshore drilling, 32% from consumers. Okay, so again, looking at this graph and not thinking about it too much, you might say, well, like the overwhelming majority of oil in the water comes naturally. There's nothing to do with humans, and so there's nothing we should really do about it. And it also says, well, like 4% comes from transportation. Look at this huge red area here compared to consumers. Like me as an individual, as a consumer, I don't have much of an influence on oil in the water, at least not apparently compared to transportation. This is obviously a visualization which has been manipulated, right? So there's no way that this green region over here, being 32% of oil in the water, is roughly equivalent to the 4% mapped out by this red area here. So someone clearly moved this graph around to get these regions to have areas that sell a certain perspective, and and then even if these numbers are correct, the message you get from a casual viewing of the areas mapped out tells something entirely different. Lie 2D, again, just changing the scales. Now we're going to invert the scale. So this graph shows the number of murders committed during firearms. And the notion is that in 2005, the state of Florida, a state is like a province, the state of Florida enacted this stand your ground law. I don't know the details of it, but I understand that if you feel threatened in Florida, you can shoot anybody you want. And people who advocate the use of guns might say this is going to reduce the amount of gun deaths, or it's going to make things safer. So you can see this graph, and I can see gun deaths in Florida in big letters, and I can see the graph seems to go up and up and up. And in 2005, this law was enacted, and suddenly the graph goes down and down and down. And your lazy part of your mind may be like, oh, I guess that means the gun deaths went down after this new law was enacted, and therefore this law must have been good, or at least not have had a disastrous effect. But like you being a smart person, look at this graph and you realize, well, the graphs are like the positive numbers are going downward, right? So the further down you go, the bigger the number. So in 2005, the gun deaths was a little bit over 500, and then subsequent to that, the gun deaths was somewhere around 750 or so. So gun deaths had a massive jump after this law came out, but a lazy interpretation of this graph would give you the completely opposite interpretation. Lie 3 is omitting data. So leaving out data points or time periods can also very drastically change the story. Sometimes this can be honest. So again, I don't want to say that things are always completely dishonest or always completely honest. Sometimes it's a mix of both. And sometimes you can even manipulate data, even in some of the ways I mentioned earlier, to actually for good effect, to emphasize real signals. So removing clear errors like outliers, maybe removing, like focusing on a particular time window, like looking at the recent past as opposed to ancient history might be more important for considering very recent phenomena. Like if you're looking at like the percentage of time people spend scrolling on their phone, it might not make sense looking back past the 1990s, for example, to the 1800s, and so on. So to be honest, sometimes you want to zoom in, but sometimes it could be misleading. Sometimes zooming in involves cherry picking only the worst or best years, depending on what your agenda is. So for this, we'll make a little fake index from 2000 to 2019. This will be financial data showing overall long-term growth. There'll be a boom in the mid-2000s, and then a recession, and then a recovery. Okay, so this is purposefully like outside of our current time period because we're not finished with our current time period, so I don't want to focus in on something that's only half done. So it's hard to tell what's going to happen in 2027, 28, 29, how the trends are going to proceed. Regardless, here's our data. Like we talked about last time, looking at this data, it's hard to see what the trend is. It's just a bunch of numbers. But we turn to visualization, and now we see some trends emerging. The full time series is on the left, but the graph on the right, we drop every other year, right? So, it's the same exact data, but I subsample every second year on this graph on the right. And I get slightly different stories now, right? So the graph on the right kind of indicates that over the long term, generally the trends are good, and it sort of filters out or washes away this big dip that happened in the mid 2010s or the early 2010s, right? There seems to be this big drop over here before things pick up again. So again, generally the overall story is a positive one, but it's still like there is a dip that is not visible here. We've removed information from the graph on the right. Does this try to hide something? Maybe someone's trying to hide the fact that there does exist some volatility from time to time. A casual viewer looking only at the graph on the right might not see any big gaps in the measurements. Like they seem to be coming in at a regular pace. So maybe I don't see any obvious malfeasance, but only looking at the graph on the right. But if we thought about it a bit more, like we might think, is there any like non-noise fluctuations happening between these data points? And a casual viewer might not be able to suspect that. Again, filtering things out in this way is not always bad. Like a lot of real data is incredibly noisy, and sometimes the overall trend can be lost in wild fluctuations. So in certain situations where you can be reasonably confident that the fluctuations you see is just random noise, sometimes filtering things out can actually be the right thing to do to convey the correct information, but sometimes it's not. So again, it's always good to try to guess at what the inherent bias or inherent interests of the producer of the graph might be. So you can cherry pick also, you can zoom in or zoom out. If someone wants to argue that the economy is in free fall, they might zoom in on only the few years here that indicate a drop. I mean, the things that actually kind of are, it's funny here because here, this kind of steep drop in the graph on the left, because it happens over a small amount of time and it's compressed in the x-axis, the drop off seems pretty severe. The drop from these years is actually the exact same between the blue graph and the red graph, but because the red graph is kind of stretched out in the x-axis, this kind of actually seems to diminish the drop somewhat. So this is kind of counter to the very effect I'm trying to mention right now, which is like, yeah, someone's trying to show that the economy is in free fall. They might just zoom in on this region where things are falling. It's obviously omitting transmitting the overall positive trend that's selling a particular incorrect agenda. But also they're doing, like in this case, they might be doing so in a way that's against their own nefarious purposes, because like stretching out this big drop actually kind of seems like it's a slow deflation as opposed to a massive free fall. Okay. Regardless, this is still like outright misinformation, right? So we're cutting out information that actually conveys elements of the truth in order to sell a particular agenda. But also we can do the opposite. We can just try to re-emphasize that everything's really good and just cut out part of the graph here that's just nothing but the positive motion after the fall. So we can cut out everything before 2011 and everything seems really great and positive. No dips whatsoever, no intermediate data removed. But this is obviously a misrepresentation of the fact. It's also true that there can be occasional drops in index value. You can omit data in other forms also. So this graph shows a pie graph. And so occasionally you might see on the news during an election, they'll show you, here's the different ridings, right? And here is riding X, and here is the proportion of votes between two candidates. So, I mean, red normally is the Liberal Party and blue is the Conservative Party. And of course, there are many different parties that exist in this country, but this is from another country in which there's only these two parties. So they might show like, oh, there's 5% of precincts reporting, and the blue candidate is winning over this red candidate. So the thing is, you look at this and then you might be on edge. You might be, oh, this is really close. Look how close these votes are right now. And this might raise your back up. This might, raise your attention to some extent. And you might suddenly be paying attention, say, oh, which way is it going to swing? Like, it hasn't been decided yet. And I want to see whether this is going to swing to the left or right over here. But if you zoomed out and showed that this is only 5% of the data. So if you zoomed out more, honestly, only 5% of the data has actually been accounted for so far. All of this gray region here has not been accounted for. It's way too early. Only 5% of precincts are reporting. Any kind of apparently big differences, and here there's no big difference really, that exists between these candidates is just maybe noise at this point, and we have to wait a long time before we get any results in. So a reasonable person would say, this is way too early. I'm not going to stay glued to the news right now. I'm going to turn off the news. I'm going to live my life, and there's nothing I can do about it anyway. So I'll come back later. My point of mentioning this is sometimes you'll see people showing all these facts at you, all these like actual factual information, but presented in a way that just is made to make you anxious or nervous or just keep you watching. Like the graph on the left is an example of this. And if they were a bit more honest, like they might be on the graph on the right, then they'd lose viewers, so they have an agenda. Their agenda is to basically get you to keep watching. So sample size is part of the problem. So consider people flipping a coin. Here's long-term over 1,000 observations. You can see the fraction of heads coming up and the fraction of tails coming up. There seems to be some kind of bias here towards tails. But if you were to stop the count, so to speak, only after like a dozen or so observations, you might observe much greater differences between the proportion of heads and the proportion of tails in your data. So there's a whole science about computing the sample size you need to be able to make any statistical claims about the difference between observations. We're going to talk a little bit about statistical testing later on in the course, but the high-level thing here is obviously like, the differences you're observing in this graph on the bottom here are partially magnified by the fact that we just haven't gotten enough samples yet. We need more data, we need more observations before we can say anything definitive. So sample size, having limited sample size is a way of omitting data. If you've only sampled 4 or 5 of your friends about their opinion on some political act, that is not indicative of the population at large. Or if you only get information from a particular social media website, that also ignores anyone who's not on that social media website. So kind of summarizing this, omitting data can sometimes be necessary if there are bad measurements or like bad noise, or if you have to really just focus on a specific question, like what's been happening within this particular frame of time is the only question you care about. But like I'm emphasizing, it can also be deceptive. It can hide volatility. It can cherry pick extreme events or periods. It can skip things that are inconvenient to your narrative. So when you see and when you make time series plots, Think about what might be missing. I say years, but what ranges might be missing. Think about how the story might change if you zoom in or out, if you extend or limit the window. Are you skipping points that might confuse the viewer in terms of overall too much noise, or might oversimplify things for the viewer in terms of too few data points? And think about just the ethical perspective, being honest about what is left out, being totally transparent, checking whether a different choice of window might tell a different story, like do the experiments, like we mentioned in module 25, and see how things will change. Continuing along these lines, sometimes people present data quantitatively, and often people think quantitative means objective, and qualitative means subjective. So like things are measurements are true and objective, and things that are like feelings and are subjective, those are like qualitative, and those are different than measurements. But if you're going out and doing surveys and measuring how do you feel on a scale of 1 to 10 on some topic, then all of a sudden you've converted that feeling into a number. And if it's a number, then suddenly you can do the somewhat duplicitous thing and start representing things in terms of graphs, in terms of as if they're quantitative. So it's mixing subjective and objective together. So you've probably seen this without even knowing it. You've seen people like surveys, well, like X% of the population is concerned about this phenomenon, or Y% of the population is excited about that phenomenon. Whether or not the population is excited or not for something doesn't say anything about the phenomenon itself. It just talks about whether what the feeling is. So I see that a lot even today. There's a lot of things happening in Canada that we see that in the news. This is how people feel about this topic. And it's still good to know. I'm not saying not measuring people's subjective opinions on things are bad, and also don't lead to particular consequences. If people feel bad about the economy, that would actually lead to them spending less in the economy. So subjectivity still matters. Qualitative information still matters. But sometimes you see graphs like this, and you see, well, how like the fear of terror attacks, and not too worried, not at all worried are in yellow, and very worried or somewhat worried are in blue. And you can see in 2014, the worried groups were like in the clear minority, but now it's almost 50-50, right? And you look at this, and I think, again, I don't have citations to these graphs, but I think the notion here is that, well, people look at this and suddenly worry, well, if people are worried about terror attacks, then something must be going on, and I should be worried about terror attacks also. Are terror attacks any more likely than they were in 2014? Maybe, maybe not, but people's opinion of it doesn't necessarily tell that story, right? So again, what is the agenda of people pushing these kinds of graphs? Is it a company that's trying to sell you on some security thing that they're selling? They would want you to be afraid, and they would kind of try to convey things in this way. Again, maybe it's a news source that wants you to be afraid, so you keep on tuning into their channel, so you stay abreast of any late developments. So their agenda is to keep you watching. So again, this is like mixing subjective things about the population's feelings on something and with actual effects are two different things. Again, like other countries, I often hear about how people are worried about crime, right? So in other countries' news, I see, well, people are worried about crime going up in big cities. And then you see these graphs, and this is the concern people have over time. And you see it's going up now. And then the message is like, oh, these big cities must have a lot of crime in it. But if you look at the actual crime rates, they might be going down in those cities. So those are two separate things altogether. They're not the same. So again, inoculate yourself against that kind of deception. And again, I'm not trying to say it's black and white. Like sometimes, if the overall mood of a population tends in a certain direction very strongly, and all of the sampling size questions have been answered appropriately, this can still have real-world impacts. I'm not saying discount them altogether, but just make sure you understand what it is you're looking at when you're looking at graphs like this. Life 5, correlation is causation. This is one of, again, the most important topics in science generally, and we'll have a whole module on correlation and causation coming up, which I'm looking forward to. But just because two things are correlated doesn't mean things are, like one thing causes the other. So there's a whole website which is linked to down here, which is all about spurious correlations. So over time, the number of people who drowned by falling in a pool is shown here in red, and the number of films with Nicolas Cage in them is in black. And you can see, well, when one goes down, the other one goes down. When one goes up, the other goes up. These things seem to be very tightly correlated. Look how close these variables are to one another. The scales are all off, but regardless, there seems to be some kind of deep connection here. So obviously this is spurious. So like it's laughable to think that like Nicolas Cage will be in more movies because people are falling into their pool. And it'll be laughable to think that maybe people are falling into their pool more now because Nicolas Cage is releasing more movies. So this is like, there's a whole website full of these funny things here. But often you'll see two variables presented side by side, and there's a very strong correlation. And then someone will kind of wave their hand and be like, well, you know, thing A has to happen before thing B, therefore thing A must cause thing B. But is that assumption actually correct? Does it actually hold? In reality, if two things are correlated, A and B, either A causes B, or B causes A, or there's another thing that causes both A and B. This is actually one of the most common things. Like in the news, you'll see people looking at two variables. People will say one thing causes the other, but then they ignore other things. Like often, like you know, a variable like overall wealth can determine someone's education and someone's likelihood to commit crimes. I'm making this up at the moment, but you see those kinds of statistics quite a bit. And it's not that education and crime necessarily are directly linked to one another, but it might be someone's overall wealth that is the cause of both of those things. A doesn't cause B, B doesn't cause A, but C causes both A and B. But also sometimes things are just accidental. So again, we'll see more in terms of this random sampling in data, but sometimes you'll get random samples together which has a strong degree of correlation, but that's an accident of just a sampling. If you were to collect the same variables again, just randomly again, then the correlation would just disappear. And that happens quite commonly. So you'll always look for confounding factors and pay attention to module 35 when we come back to it. Lie 6 comes back to some problems of human perception. We talked about how humans are not very good at looking at like slight differences in context. So here is the reputable New York Times looking at fuel economy for automobiles going from 1978 all the way to 1985. And they had an example of form over function. So they made this graph look like a cute road with this dashed line in the middle. It looks like a road. We're talking about cars. Isn't that cute? And then they have real data. So in 1978, the fuel economy down here is this line over here, and the fuel economy of 1985 cars is down here in 1985. And then they have like the fuel economy proportion like over here on the right. Like the miles per gallon. And so it looks like a road, and you can see it appears right now that as you get closer and closer to the present, the fuel economy is growing by huge orders of magnitude, ignoring the numbers, which again, looking at numbers don't mean much to our human brains, but looking at extents of something, lengths of things, is something our pre-attentive, occipital lobe picks up on. Now, the actual miles per gallon change from 18 to 27 and a half is an increase of about 52%. But the length change from 1978 to 1985 is an increase of almost 8 times, right? You can measure this yourself if you want. I can't remember how I computed this, but the difference between 18 and 27.5 is obviously not multiples of 18 all the way across, but it appears that way visually. Like, look how well we're doing in 1985 compared to 1978. But in reality, the differences are much smaller than what is conveyed here. Okay, so the perspective is confusing. Everything's been stretched out of whack. This is another lie. Biased samples. Again, this is having to do with sample size. Here, this graph says the President Trump's job approval is 88%, which sounds amazing. This is from his first term. So someone with bad eyesight or limited attention might not be able to see that this is among Republicans here. So technically this is true. There's no outright lies going on, but this is only zoomed in to people who are Republicans. If you zoomed out and included Democrats or people who are neither of those two things, like you get totally different measurements, which I've not shown here, but you can read more about it at this link. All right, so again, so first of all, people might not even notice that there's small print here and just see that almost 90% of people approve, and that's the only thing they understand, and that's unfortunate. But even if you did read the among Republicans, there's also a subset of us in the population which might not really care, right? Like we see this, we know that it's only among Republicans. We don't take the second moment to think about what I just mentioned before. What about Democrats? What about independents? Are things changing? So being self-aware, being aware of any kind of cognitive biases is also incredibly important to keep in mind. So I want to work through a couple of examples with some code for you to play around with as usual. The first one just goes back to the truncating the axis question. So here we have some polling data from a few months. We only have two samples here. In January, the polling was at 48%, and then it's at 52%. If you visualize these two things, you can change the axis, the y limits from 0 to 100 or 45 to 55. And again, you get either very little difference between January and February or an awful lot of difference between January and February, depending on whether or not you've zoomed in or not. So how big does the change look in each panel? If you were a campaign trying to hype a tiny bump, or I shouldn't have got ahead of myself, but if you're trying to hype up the difference, which of these two graphs is telling you what one is the biggest difference? And are any of these graphs lying? And in which direction are these graphs lying, quote unquote, with the numbers? There's something from Tufte called this idea, which we're calling the lie factor now. This is like the amount of visual change in proportion to the amount of data change. This also applies to the miles per gallon graph I showed you a moment ago. So in our polling example, the actual data is a difference of 4 percentage points between 52% and 48%. But the visual change is the actual distance between the height of the plotted range as we've shown. Okay, so the difference in the chart between 45 and 55. So here, I've shown from 45 down here to 55 up here on the right graph. This is a difference of 10. The range is 10 points. So the perceived difference, this difference from here to here, is 40% of the overall vertical difference. That's 0.4. Okay, so that's the perceived difference, the visual change. If you compare the honest chart against the truncated chart, you'll get very different differences here. The honest chart is 4 out of 100 compared to 4 out of 10. For the full scale, there's 0.04 versus 0.4. The truncated or zoomed in chart makes the effect look about 10 times bigger than the full scale bar chart. So I'm not necessarily saying that the truncated chart is the one that's lying, but it helps to elucidate these differences. These differences are meaningful to an order of magnitude, and this can tell you if the lie factor is wildly positive, more than 1 orders of magnitude, or if it minimizes things to some degree less than 1. And again, you can ask yourself, am I helping or distorting the truth? Example 2 is using area wrong. So here you can see we have a small array where we have measurements A and B. A is 10, B is 30. So B is 3 times A. That's all we're really conveying. In this first graph, you can see we're just plotting things out linearly, and the widths of these bar graphs are the same, and the only thing changing is the y graph. On the right, we're changing not only the height, we're tripling the height between A and B, but we're also tripling the width between A and B. So technically, we're not lying here, so B is still 3 times taller than A, but visually, the overall impression we get subconsciously is that B is, in this case, polynomially or quadratically larger than A, right? We get a 3 to the squared because the overall area is 3 times 3 times bigger than the area A. We get a very different interpretation of the graph on the right compared to the reality on the left. This happens occasionally too. So people will manipulate, an axis that doesn't actually convey anything. In this case, the label. They'll just manipulate that in order to sell whatever agenda they're trying to sell. Example 3, colors, contrast, and accessibility. So I kind of touched on colors very briefly earlier, and also in the previous module. I just want to highlight, for one thing, sometimes color choices can carry cultural meaning. In the West, including Canada, often red indicates danger and green indicates safe. So red is bad, green is good. But in some countries or cultures, red actually is good, or red indicates maybe luck or prosperity. So depending on who your audience is, you might want to be aware of that. Again, in the previous module, we talked about the why question, who your audience is. So that's part of it. So even something like that is important, and it feeds into your visualization. It can be hard to, sometimes small differences between red and light red might be very poorly distinguishable. And just from the point of view of ethics and accessibility, it can be invisible to some individuals. So for some individuals, they have a red-green blindness. All of these 4 groups would appear visually to be the same. right? So like whatever red and green is measuring over here, someone with that like ocular difference would not be able to capture that. Also, I mean, my own advisor when I was a grad student, we kept on pointing out when my graphs would say like, well, if I'm going to do his accent, he was an Australian man, but he'd say, well, it's so hard not to do his accent. He would print out the my papers and he'd show, well, these two, like in color you can tell the difference, but when I print it in black and white in grayscale, the difference goes away. This is bad. Do it again. And even back then, I'd say, well, most people are looking at these images on their computer anyway. No one's printing things out anymore, but that isn't true. You always have to keep in mind that sometimes we'll be dealing with people who have color blindness or people who are looking at black and white or grayscale printouts, and so on. It might be more accessible to also not just change the color, but also include a pattern. So, change color from blue to tannish, but also include hash marked so that even if you print it out in a grayscale, the difference will still be obvious. And then rates, this goes back to the earlier thing we were talking about or complaining about, I guess, with regards to absolute versus relative terms. Raw counts can make big populations look as if they're the worst, even if per capita they're actually maybe even the best, right? So here's 6 fake regions, north, south, east, west, city, and rural, in terms of case counts for some disease. In absolute terms, well, the city has 1,000 cases. And the western shore only has 180 cases. I guess the city, I mean, like this, yeah, I'll get back to this in a second. Something bad must be, like whoever is running the healthcare system in the city must be doing something wrong, right? And we need to get good Western, Western team should go and help the city. But if you consider the fact that, well, there's just more people in the city, so of course rates are higher, then things change quite drastically. And then you can see actually these rural areas have much like a higher proportion of cases relative to the population size. So it isn't about density, it's something else is going on here. Maybe density actually helps getting people the resources that they need. Maybe there's too much emphasis in the city at the cost of the rural communities. So maybe what we need is not more help going from the west to the city, but we need help from the city going to rural areas. Again, like I don't want to just paint this as a black and white, binary kind of decision. Because indeed, sometimes it could be the case that cities actually have higher contagion rates, and therefore they just need higher degrees of attention. That is not for me to decide, but when I'm conveying information to the members of my team who are on the healthcare community, like we need to know what we're looking at in order to make sure we can make informed decisions. And finally, the pie versus bar chart again. I think most people hate pie charts for many reasons. I see them sometimes. I see sometimes students who are, very, amateurish when it comes to data visualizations. They'll put things into a pie chart, and that'll be the end of it. We saw that with Florence Nightingale actually in the previous module. There are issues with pie charts in the sense that, like, regions that are mapped out in this way overemphasize differences in terms of their perimeter compared to regions towards the center. A 20% difference will look a lot bigger along the edge here than it would just in the smaller component in the middle, again, because of humans' inability to differentiate between regions appropriately. But just visually here, like even like this is kind of an optical illusion. The numbers here are exactly the same. The graph on the left might kind of indicate that the Chrome browser, being used by 63% of people, is approximately half. It's not necessarily a monopoly. There's no cause for alarm over here. Safari is still a very big competitor to Chrome. But if you were to plot the same exact data in a bar chart here and sort it from biggest to smallest, you would see that, well, there's several multiples of Safari fit into Chrome. And like there seems to be a lot more dominance, at least to me visually, between Chrome and the other browsers here in the right graph than the left one. So again, the same data can tell different stories. Complete dominance, at least to my eye, on the right, and maybe a bit more competition on the left. So I want you to think a little bit. Which chart makes it easier to see the difference between Edge and Firefox, right? Where is it easiest to spot everyone combined versus Chrome, so other plus Firefox plus Edge and so on. And if you wanted to, like if you worked at Google for some reason, and you wanted to make Chrome's dominance look less overwhelming, which chart would you prefer to sell that narrative? Final thoughts. So again, this is part of the reason why this is such an important module for me. We want to be able to tell if somebody is trying to lie or trying to be deceptive, or even being deceptive accidentally with statistics. Okay, it is crucial to detect and avoid these misleading behaviors. If there's inaccurate communication, if there's real data but it's communicated inaccurately, this will lead to poor understanding on the part of whoever's receiving it. Then that person will make faulty conclusions. You know, they might decide to spend resources in an area that doesn't need it. They might vote for a candidate that is against their interests. This results in bad decisions and bad consequences, and then therefore a worse world. I'm obviously not saying that all of the problems we're observing in today's world is because of bad visualizations, but when it comes to making decisions as a population, we tend to make those decisions on how we communicate to one another, and what we choose to communicate and what we choose to avoid communicating, and how we choose to communicate information as crucial as statistics can lead to very different decisions. And if those decisions are wrong, then things will get worse. Okay, so I can't emphasize how important it is to get this right. Your individual careers are almost certainly going to involve data analysis in some way, whether or not you're data science as core or data science as a tool. Data science will be a big part of it. And you're going to have to generate graphs or interpret graphs, and you want to make them ethically, and you want to interpret them carefully. And generally, even as a citizen, our lives are going to be dominated by data. Like, what does it mean for this economic measure to be this or that or the other thing? This is all expressed in terms of data. Just as living your life generally, data will be a big part of it. So it's important to get the skills in understanding data and thinking about it carefully. A key habit to generate is, asking what isn't being shown here. If I'm getting some information from this person, what is their angle and what might they not be telling me right now? And how can I go about getting that information that might be not conveyed at the moment? When you're making plots yourself, label things clearly and as simple as possible, but not simpler, as the saying goes. And avoid cherry-picking ranges. But if you do, make sure that everything's documented, everything's transparent, and explanations are clear, accessible, and front and center when they need to be. There's two biases I want to talk about. So I might come back to just basic thinking as a topic later on in this course, but it's relevant to what we're talking about now. The first is the Dunning-Kruger effect. You might have heard of this. The Dunning-Kruger effect basically measures someone's confidence in their skills versus their actual competence. And the story goes, this is an oversimplified version, is that people with very low competence will still think that they're expert in something. Again, I don't want to get into this too much, but you hear a lot of people talking as if they're absolute experts in immunology or epidemiology, and they'll have these massive, loud debates online or in those stupid YouTube videos or with other people around the kitchen table, wherever. They know nothing about epidemiology, but they'll talk with a massive amount of confidence. So they're way down here in this end of the spectrum, very low competence, very high amount of confidence. These are extremely annoying behaviors, but we see that overabundantly large amount of the time. As you increase your competence, so as you go through courses hopefully like this and others like it, and increase your competence and become a wiser member of society, then your confidence will actually go down. You'll start to realize the mistakes you were making, and then that will kind of open up to the fact, wait a second, I'm missing a lot of stuff here. My assumptions were wrong. There's so much more stuff I didn't know about yet, and you start realizing, I actually have I have a lot more to learn, and you'll drop your confidence will drop as your competence increases. And this is sort of framed sometimes as a paradox. How could your confidence go down while your competence goes up? Anyway, the other side of the story is that at some point you'll become an expert in something. Your actual competence will be like, say, 80%, whatever that means. And your confidence might go up again. I'm an expert. I know what this means. I can interpret this graph. I can interpret this measurement, and you can go out and now reasonably be part of the conversation again. But again, there's always going to be more to learn. There's, I think it was Socrates, if he even existed, who said, I'm only wise because I know that I know nothing. That's an important idea to have, right? Like, never think that you know everything. And as a scientist also, if you think you have the truth, always think that no, you don't. There's always more you have to seek out. So another warning: people with low skill can overestimate their ability, and highly skilled people will underestimate how exceptional they are. And here's a paper about it. So to get around this, consult with experts. Keep on asking questions. Seek and listen to constructive feedback. Stay humble and stay curious. These are two extremely important messages for everybody. I want to just highlight here that sometimes I find that people who are like in the area of a first-year class in computer science might feel that they already know everything they need to know about computers because they know how to update their computer and they know what to click on the proprietary software in order to get it to do what you want. But that's not computer science. That's not a fulsome understanding. There's an awful lot that you just don't know yet. And it can be anxiety raising to suddenly realize, oh no, there's all this other stuff I've never even heard of before. I mentioned the command line in the very first lecture of this class in person. And this can sometimes be scary to people. And then people can get entrenched and say, no, I don't need to know anymore. I already know all I need to know. I'm already I'm more knowledgeable than my family members in computer science, so I'm already an expert. But that means that you're kind of at this end of the spectrum. You're high degree of confidence, or at least high degree of like you're convincing yourself of your confidence, but really there's an awful lot more you need to know. So, this is a cartoon version, but the Dunning-Kruger effect is real, and you need to make sure that you're not trapped in it. The second important thing is important for everyone on Earth to know also is the confirmation bias. This is the tendency to seek, interpret, and remember information in ways that confirm your existing beliefs that might downplay or ignore evidence that contradicts it. There's a paper you can read about it here. So in data science and machine learning, this means like only plotting metrics or time windows that support your model. Like if you believe something to be true, you construct a visualization that explains that thing you think is true. But along the way, you've subconsciously kind of removed things that disagree with your interpretation or your expectation. That is bad. Like doing lots of experiments and then finally getting an experiment that you were looking for this whole time and then stopping and saying, I finally found the truth. That's wrong. You stopped because you found something you like. Keep going to make sure this is correct. Searching for evidence that a pattern is real is an old-fashioned, non-scientific way of doing things. The way that science works is through disproving things. Like always try to break things, even if it hurts your feelings. Try to find ways in which your theory is wrong. That is important in science, and it's also because science and scientific methods are so important in our society now, it's important as a citizen as well. You can mitigate against the confirmation bias sometimes. In science, it means pre-registering your hypotheses. So claim what you expect to see first and then do the experiment. So then you can't go back and fiddle with your hypothesis after the fact. Again, deliberately look for disconfirming evidence. Keep on trying to prove that you're wrong. Do error analysis, try to find counterexamples and so on. And use so-called blind or automated evaluation procedures whenever possible. So make sure your thumb is not on the scale. This is from a scientific perspective. I think you can imagine how to avoid confirmation bias in real life. But yeah, that might mean if you have a favorite politician, a favorite celebrity, and you hear that they do something that you don't like, it's important to not be like, well, I don't believe that because I like this person, so I'm not going to believe this bad news. You're just looking for, it's a form of confirmation bias. You're ignoring information you don't like because it doesn't fit with your worldview, and that is incorrect. So confirmation bias is a way to lie to yourself with data, even when no one is actually trying to be dishonest. And again, if you're getting information from a source that also has the same confirmation bias that you do, or if they know that you have that bias already, they can exploit it. So just be careful when you're getting information from sources that might take advantage of you in this way and lead you down one path or the other for their own purposes. So as a future data scientist, as an analyst and engineer, and I'd say as a human being also, make sure that your charts or any kind of things you're putting out into the world, you're going to be doing that. You're going to be telling people your opinion. You're going to be making charts. You're going to be reading charts. You're going to be hearing opinions. Doing this ethically and responsibly means making sure you're choosing representations and encodings that support the true story of the data as best as you can approximate the truth. Being upfront with your uncertainty and limitations, it seems to be that this is what the data is saying, but I can't be sure. It's important. Like, being uncertain is not a sign of weakness. It's not a sign of lack of confidence. Like, if going back here, if you're couching all your claims in what ifs and maybes, and at least that's what the data seems to say, that kind of language means, like, I'm more likely to believe you as someone who knows what I'm talking about. Again, not me personally, but as an example. Avoid designs that exaggerate tiny effects. Avoid designs that hide big ones. A good rule is, like, basically, if you'd be embarrassed to show, like, the raw data to somebody next to your chart, then the chart might be misleading. Here's a little honesty checklist for your plots. This kind of combines the previous module in this one. Before you ship a visualization, if you're looking at bars, does a y-axis start at 0? Is that reasonable? For lines, is the scale and aspect ratio reasonable? Is it clearly labeled? If you use log or percentage scales, like, is that indicated? Is it justified? Like, are you using percentages or logs because it's hiding something? That would clearly be nefarious. Are you using position or length, properly, instead of, like, area or, like, three-dimensional fluff, which we didn't really talk about, but sometimes you get three-dimensional graphs which, like, overemphasize certain things in a way that's also wrong. Are you using color in a way that's accessible to people and intuitive? Like, are you darkening or lightening things in a way that actually conveys information, or are you trying to misguide people? And are you using more than color to tell categories apart? Something to consider. Are you omitting data, or are you adding too much extra data? Is the sample clearly described? Is it documented carefully and clearly? All that's important. And does the title or caption match what the data is actually supporting? And is the story maybe the result of an agenda, either someone else's or yours, right? Again, this touches on the confirmation bias. Do you want something to be true, and are you producing things that tell the story that you wish is true? If you're not even aware of that, that means you're too immature when it comes to data science. If you are aware that you have a bias and you're kind of aware of how you might be manipulating your data in a way that feeds that bias, then you're more mature. And if you're aware that you're biased and you don't care if your story might not demonstrate the truth, then you're immoral, you're unethical, and I trust that none of you are in that category. If any answer is making you uneasy, then rethink things. Here's your quick check on the slides posted online. In summary, human perception is powerful in some ways. We have a lot of automatic processing. We didn't talk about neuroscience today, but there's a lot we can do very well. But this also means we can misjudge things like areas, angles, colors. We can succumb to optical illusions and cognitive biases. Designers can accidentally or intentionally exploit these flaws by truncating, inverting axes, having weird scales, overloading pie graphs, otherwise having misleading graphs. So, like, visualizations, even if they're pretty, it doesn't mean that they tell the correct story. Your job as a practical data scientist and your job as an ethical member of society is, don't put things into the world that you know is misleading. Do be suspicious and curious about other graphs you're seeing, including from people that you want to trust. That doesn't mean, like, be skeptical and be outright a conspiracy theorist. That's also, like, a form of cognitive bias and can be unfortunate. But it's good to ask questions. Use simple, honest encodings. Use an ethics-aware checklist like the one I just mentioned. And the main thing is always try to find the truth, even if it means dropping what you previously thought was the truth, and doubt that you found the truth, and doubt other people who claim that they found the truth also. We have a good amount of citations for you to dig into here. As always, it's a pleasure. See you next time.